Hello everyone, today I will present this paper called Quadratic-Bound-based Kernel Density Visualizations. I'm the first author of this paper, please call me Edison. I'm currently the postdoctoral researcher in the University of Hong Kong. First, why do we need to use kernel density visualization, KDV? Kernel density visualization has been used in many different types of applications. The first one is that we can utilize kernel density visualization to visualize the COVID-19 cases. And you can see that if the color is green or the color is red here, this indicates that there are more confirmed cases in these regions. And the second application is to utilize the kernel density visualization to visualize the crime events. And the red color indicates that there are many crime events in this region. And after I talk about two different applications, I would like to mention what is kernel density visualizations. Here I use the crime rate predictions as an example to illustrate the concepts. First, you can see that there's so many black dots here. Each black dot represents the location of a crime, for example, robbery, commercial burglary, or motor vehicle thefts. And our goal is to predict the crime rate of a given location Q based on computing the kernel density functions FPQ. And the kernel density functions can be found here. After we compute the kernel density functions value for each pixel Q, then we can classify or color pixel Q based on the value of FPQ. And consider this part. The value may be, the density value may be very low here, so we can use the green color to represent it. Consider this part. You can see that there are so many crime events here, so we can the FPQ can be very high here, so we can use the red color to color it. However, evaluating exact KDV is very expensive, as pointed out in this paper. Computing the exact density function of 1 million points on a 2 megapixel screens requires 2 trillion operations. That's why we need to use some types of operation or approximations to make it faster. That's why in our paper we focus on one type of approximations. This is the threshold kernel density visualizations, and instead of evaluating exact kernel density function value for each pixel, we return or we classify the value to be a high density or low density in this figure. So that's why we have these figures. This yellow part represents the higher density regions, and this black part represents the low density regions. And now, after we have these approximations, then you may ask, how can we achieve the split up based on these approximations? And here we propose, we utilize the concept of the bound functions to help us provide the split up. And the bound function, there are two requirements for the bound function. The first one is that they should be fast to compute. That's meaning these two bounds must be much faster compared with this FPQ. And the second one is that this bound function should be as tight as possible. And then you can ask, even you have this lower bound, upper bound, how can we achieve the split up? And consider these two cases. Suppose that the lower bound functions is the value of the lower bound function is bigger than this threshold tau. Then we can immediately conclude that this FPQ is bigger than tau. We can classify as a high density. If the upper bound is more than this threshold tau, then we can immediately classify that this is a low density. And you know that if lower bound, upper bound, they are fast to compute compared with this FPQ. That's why we can avoid computing the exact FPQ. So this is the reasons how we can achieve the split up, because we can avoid computing the exact FPQ, which is very expensive. And now we illustrate the concept of state-of-the-art bound functions. And the state-of-the-art bound functions, the concept is here. And you use the exact kernel density functions here, and we regard this gamma distance QPI squared as a value xi, and this function becomes exponential minus xi. And you can see that we plot this function. Oh, sorry, we plot this function. And then you can use this example, use magnitude P equals to 3. That means the data set has only 3 points as examples. And now you use the linear line to approximate or to act as the lower bound of these exponential functions. And you can see that once we replace these exponential functions by this linear line mx plus c, then this FLPQ ln MC should be, or sorry, must be the lower bound function of this FPQ. But you know that the complexity of this FPQ is O magnitude P times D time, and this one, after you read this paper, then you can know that this OD time, which is much faster compared with this time complexity. Then you may ask, this seems to be a good solution, but in fact it's not. Suppose that this x1, x2, x3, they distribute far away from each other. Then you can see that this approximation may not be good. You can see there's a very large gap here. And this can provide us a very loose bound for this excess kernel density functions. So the question is how to reduce the gap. That's why we need to have this paper called, instead of using the linear line to approximate this exponential function, we use the quadratic function to approximate these exponential functions. And you can see that this quadratic functions can be much tighter compared with this linear line. Then you may ask, yes, this is good because it's tight, the bound is tighter. But what is the time complexity of called? If it is very time consuming, then it's still not useful. That's why we focus on the time complexity here. And the idea is simple. You replace this exponential minus x by this function ax squared plus bx plus c, which are quadratic functions. And you can further expand these terms, and you can find that the time complexity is OD squared. For details, you can refer to my paper. Then you may ask, OD squared is worse than OD because and that thing is worse than the state of the art one car. But you know that this paper focused on the visualization applications, and human can only visualize at most 3 dimensions. That's why the dimensionality D of the dataset is most 3. That's why OD squared is nothing compared with OD. This explains, but you know that this bound functions is much tighter compared with the existing bound. That's why you only need to pay a little bit, but we can achieve much tighter lower bound functions. This explains why our method called can provide much better performance compared with the state-of-the-art solutions car. And this is experimental results for IKDV in 4 large-scale data sets. And you can see that our solution core can provide at least 1 order of magnitude speed up compared with the state-of-the-art solution car. And now we can try to move our research work into the real product called IKDV-SYS, which is based on the technique. We developed a system called IKDV-SYS. And now we can use this to visualize the COVID-19 cases. And you can see that it's a USA, and you can see that this part, there are more confirmed cases here. And you can, in our system, we can zoom in, and then you can go inside and visualize this part. Should be Chicago. And steps is zoom into this part, and then we run it, and it's very fast because this system uses our techniques. And then you can further zoom it to the city levels and visualize the details information. And if you're interested, you can go to our project link, and this is the video link to show you our systems. And now we go to the conclusion. We want to conclude and propose our future, but the first one is that we will provide a theoretically tighter bonds compared with car. And our method can achieve at least 1 order of magnitude speed compared with the state-of-the-art solutions. In our future way, we propose 5 future ones. And the first one is, can we support some important and timely applications using car? In fact, we have done that. Can we support, the second one is, can we support other types of feature-based kernel functions? In fact, we have also done that. The third one is, can we extend our methods to training phase of kernel methods? And the fourth one, can we support other types of kernel-based models, kernel clustering, for example, or kernel PCA? The fifth one is, can we support the prediction phase of graph-based kernel methods? And this one we have not started, and we are starting as soon as possible. And this is the end of our presentations. And if you have any questions, you can also email me. Thank you.